Hi. Let's continue our studies about the different operations over the vectors. Now I wanted to consider the following small thing: components of a vector. So consider vectors, say, in the plane. Vector A with components A1, A2. We can find A1, A2 in the following way. A1 equals A dot I. A2 equals A dot J. So here I and J are the basic vectors. These vectors I, vector J, and so we have, if you take any vector A, then its components are given by these dot products. Now we can also consider vector A and any other vector, say U. U is a unit vector. Unit vector means that its length or magnitude is 1. And then we can write component of A on U is simply A dot U. Yeah, so this is the formula for component. Now, a little more general is the following. If you have, say, vector A and any vector B, let us define a unit vector in the direction of B. Say this vector U. U equals B divided by length of B. And then we can write that component of A in the direction of B equals A dot U equals A dot B divided by length of B. Yeah, these all are definitions, or if you wish, notations. This operation component will be used a little later. So this is component. Now the projection. Of A on the direction of B. So if you have vector A and we have vector B, then this projection is, we take the orthogonal projection of the endpoint of vector A on the direction of vector B. So, and this is vector C. C equals projection of A on direction of B, or simply on B. So how can we find this? Let us denote U equals B divided by length of B. So it is the unit vector here in the direction of B. Then what is C? C is length of C equals length of A times cosine phi. What is phi? Phi is this angle. Yes? This length of C, and then so this means that C equals length of C times U equal norm A times cosine phi times U. But what is cosine norm A, length of A times cosine phi? Length A times cosine phi equals, we can write length of A times length of U, because U is a unit vector, U is here, times cosine phi equals A dot U. Yes? And so C is A dot U times U. This U. But what is U? U is B divided by length of B equals A dot B divided by length of B times U is B divided by length of B. Equals A dot B divided by magnitude of B square times B. The magnitude of B square equals simply, so it is A dot B, B dot B times B. So this is the answer. So projection of A on the direction of B is given by this formula. Let me write it once more. projection of vector A on vector B is A dot B divided B dot B times vector B. So this is a scalar, this is a scalar, and this is a vector. Now, for example, which example I did? For example, I will take another pen. Example, A equals, say, 1, 2, and B equals 3, 4. Yeah, it is 1, 2, it is this, it is A, 3, 4, it is this, a little more, it is B. Then projection of A on direction of B equal, let us A times B, it is 1 times 3 plus 2 times 4 divided B dot B, 3 square plus 4 square times B, it is 3, 4, yeah, equals 3 times 8, it is 11, divided by 9 plus 16, it is 25, times 3, 4, equals 3 times 11, 33 over 25, 44 over 25. Yeah, so it is this vector. It is projection of vector A on vector B, this vector C. It is C. That's it. So, as I said, we will use this operation, and that time I will remind you a little later, after we go through some other things. And one more thing, all these formulas work in 3 dimensions as well. So in 3 dimensions we have vector A and B, we define by the same formulas projection and component, and it all works. Yeah, so it is valid in 3D as well. The next operation is much trickier and much more interesting. it is what is called cross product. It is defined for vectors in three-dimensional space. We have two vectors, A and B, and the cross product is another vector, third vector. This operation has quite different properties and is far from obvious. It is much more involved than the dot product. So to explain it, I need several preliminary steps so that you can use it and explain several other things before. So let me start from elements. No, let me start from the beginning. Consider vectors in the plane and consider pair of vectors A and B. First, I defined what is left and right pairs of vectors in the plane. I'm sorry, it does not write. My pens are bad. So consider two vectors in the plane, vector A and vector B. So what can be simpler than pair of vectors? But it turns out that there exist two different sorts of pairs. So consider this, the vector which is the angle between vector A and B, which is smaller than pi, than 180 degrees. And consider in which direction should we rotate vector A so that its direction eventually coincides direction of vector B. So here is this direction, because this angle is less than 180 degrees. You see that we need to turn it counterclockwise, vector A, so that its direction coincides with direction vector B. So in this case we call this pair right pair. A, B. This right pair. But we can have this situation, this vector A, and say this is vector B. In this case, if you rotate vector A in the plane so that it eventually assumes direction of vector B, then we have to turn it clockwise. Yes? So in this case we have the left pair of vectors AB. No, certainly if AB forms a right pair, then BA is left pair, and conversely, if AB is left pair, BA is right. So the different pairs of vector are either right or left. Exceptions are if the angle is already 0. Yes, so if A and B have the same direction, then we cannot say it is right or left, it's degenerate pair. Or if they are anti-parallel, the angle is 180 degrees, then it is also, we cannot say it is right or left. So, but these two cases are degenerate, and in the interesting cases we can say that either this pair is right or left. The next thing which is important by itself is what is called signed area of a parallelogram. Defined by the vectors A and B. So let me explain what it is. Suppose we have two vectors, say this is A, this is B. Let us draw the parallelogram. Complete these two segments to the full parallelogram and consider the area of this parallelogram, just the area. The signed area, so I take A, which is defined by vectors A and B, equals the following. If A, B form a right pair, then it is usual area if the pair AB is right, or minus usual area of the parallelogram if the pair AB is left. Minus, so the area can be positive or it can be negative. Yeah. No, we can regard positive area, say, as just area of a piece of paper. Yes, it is positive area. What is negative area? If you make a hole in the shape of parallelogram, then we can count this area of the hole as negative area. Yes, because it is what is deficient in the full sheet of paper. So it is like with other situations when you use the negative numbers. Say if you have some amount of money in your pocket, it is positive amount, but if you have a debt, yes, you took a credit and cannot return it, then what you have is negative amount of money. Yes, the same with the area. Area can be positive and can be negative. And it turned out that this area, which can be called area with sign or signed area, has is much more behaves much more regular than the usual area. So next is the question how to find the area of this parallelogram, the signed area. It is a function of two vectors A and B. How to find it? What is the formula? So let us start to look for the formula. So suppose vector A has component A1, A2. B has component B1, B2. To find the area, I prefer to do it step by step through the properties. We find some properties of this function area, and then the formula will go as it is by itself. So properties of the function area of a parallelogram defined by vectors A and B. So the first property, A of AB equals minus A of BA. So if you change places of A and B, the signed area changes sign. No, simply because if you take a right pair of vectors A and B and change places, then the pair BA is left. Yes? So the area changed sign. If this is left pair, this is right pair. Yes, so it's quite symmetric. So this function, I would say, is antisymmetric relative to transposition of arguments A and B. It is a new property. If you recall, the dot product was symmetric. Dot product of A and B was symmetric. So it is also a sort of product of A and B, but different. It is not dot product. Second property, if you multiply one of them by constant k, by number k, it is k times area of AB. So it is linear with respect to the first argument. Now, how to prove it? Let me draw a picture. It is vector A. This is vector B. And the signed area of this parallelogram is the area of AB. Now, if you replace A by KA, so multiply by k. Here we have two cases. One case is when k is positive, other if it is negative. So if k is positive, you will have a vector, no, say this vector. It is k times A. Yes, and corresponding parallelogram defining area, which is function A of KAB, is the area of this parallelogram, signed area. Yes, and because this vector has the same direction, it is parallel to vector A, and B also is the same, then the area of parallelogram, by the elementary formula for the area of parallelogram, is proportional to the length of A, so it is proportional to K. So in this case we are done. Other case is when K is negative. If K is negative, so this is vector Ka. K is negative, and we have this parallelogram. This blue parallelogram, and in this case vector Ka and B form a pair which is if pair AB was right, this pair KAB becomes left. Yes, as you can see from the picture, if the pair was left, this pair becomes right. You can draw another picture and have this situation. Yes, so in this case the theorem also easily follows. Let me skip too much details, because it is a sort of theorem which becomes less clear if you tell more details in the proof. I think you can restore it yourself. Another next properties. Next properties is the following. Area of A, K times B equals K times area of AB, which is demonstrated in the same way. It is the same. These two properties I write under the number 2. Number 3. A plus B C equals AC plus area of BC. So distributive property. And similarly, area of A B plus C equals area of AC plus area of BC. We can write this also. Let me consider the first. Why we have this distributive property. To this end, let us consider the picture. It is sorry, I need a little more space for this. So we have to consider three vectors, A, B, and C. So this is vector A, this is, say, vector B, and this is vector C. So vector A plus, one moment, let me a little shorter. Vector A plus B, let me draw it in red, this vector D equals A plus B. and our first area of DC of A, or A plus B C, is the signed area of this parallelogram. No, maybe a little this one, this parallelogram. So parallelogram, let me denote it. O P Q R. So the left hand side, A of A plus B C equals signed area of parallelogram O P Q R, of this parallelogram. Now the right hand side, DAC, it is the area of this parallelogram S. So area of AC equals the signed area of parallelogram O S U O U S R O U S R. Yes, this parallelogram. A B C equals signed area of parallelogram this B C of this parallelogram parallelogram U P Q S U P Q S of this parallelogram. Now observe that so the sum of these two areas is the area of this domain, which is the union of two parallelograms. And this domain, what is the difference between this domain, the area of this domain, and the area of this parallelogram? We added this triangle RSQ and subtracted this triangle OUP. Yes? And these two triangles are equal, or somehow they have the equal area. They are obtained by shift. Yeah? So they took parallelogram ORQP and added area of this triangle, subtracted the equal area of this triangle, so we got the same answer. Now, here I considered simplest case when all the pairs of vectors are right, and so all the areas, signed areas, are in fact simple areas. Yeah? We have to consider other cases when some of these pairs are right, some are left, but you can do it yourself, so it requires a little more time, but the result invariably is the same, and this is the force of the signed area. So this is more or less all. So let us assume that these properties hold, and then I can easily derive the formula for the area of signed area of parallelogram. Let us look. So suppose we have two vectors. Yes, I did not write the fourth property of signed area. So consider two basic vectors. Vector I equals 1, 0, and vector j equals 0, 1. These two vectors. So signed area of ij, so we have to consider the area of this unit square, and the ij form a right pair. So it is 1. Correspondingly, area of ji equals minus 1. This minus. Now, area of I, so we consider two vectors, I and I. No, certainly they they generate parallelogram having 0 width, so its area is 0. And area j is also 0. And at last, suppose we have two vectors, A with components A1, A2, and vector B with components B1, B2. Yeah? So area of AB equals area of A1I plus A2J, because vector with components A1, A2 is simply vector A1I plus A2J. Here B1I plus B2J. Now we know that the function area is linear with respect to the first argument and linear with respect to the second argument. So this means that we can open these brackets and write the following: area of A1I, B1I plus area A1I, B1J plus area of A2J, B1I plus area of A2J, B2J. Which is equal. Now, we know that this is equal to A1 times B1 times A of II, A1 B1 A of II plus B2J. A1 B2 area of IJ plus A2 B1, it is here, area of JI plus A2B2 area of JJ. Now the last stroke. Here at this place was written the values of the function a of these basic vectors. So area of II is 0, area of JJ is 0, area of IJ is 1, area JYI is -1. So what remains is A1 B2 minus A2 B1. This is what remains, and this is the answer. Equals, so we can write in the following form: A1 A2 B1 B2. It's a determinant. At last we have a determinant, and we will see maybe different determinants in this course, no, close to 100 times. So after all, you will be very used to such monster as determinant. In particular, we can see the origin of determinants, at least of determinants of order 2. My early experience with this subject was very, I would say, difficult, because I did not understand why determinants are such a queer function, so that we have to take this product, criss-cross product, and with different signs. Why? What is the justification of this? It looks like a really queer definition. And here we see how this thing appears. What is the origin of this, or justification, or explanation? Determinant is simply a signed area of the parallelogram. Moreover, if you are interested just in the area, not in the signed area, you will have like S, it is the usual area of a parallelogram, then you will have the following interesting formula. You have to forget the sign of the signed area, yeah? So S of AB equals absolute value A1, A2, B1, B2, yeah? So the, I would say, graphical image of this formula is really strange. But nonetheless, we'll have this formula as well. Now, consider example. Small example. A equals 1, 2, and B equals 3 minus 2. What is the signed area of AB? It is 1 times minus 2 minus 2 times 3 equals minus A. minus 8. If we have the negative signed area, this means that vectors A and B form a left pair. Now let's see how it looks. 1, 2, it is approximately this vector. No, just a minute. Yeah, no, this vector. This is A. And 3 minus 2 is this vector. This vector B. And you see that to get vector B from vector A, direction of vector, we have to rotate it clockwise, this direction, clockwise. And this means that really they form a left pair. Not right pair, but left pair. So, this is left pair, so the signed area of this parallelogram is negative. Okay, so this was I would say, the first part leading of the way leading to the definition of cross product. So the definition will be in the next lecture. For now, let me say you goodbye, have a good time, bye.